Your car will rust, your roof will leak, your phone will age out of updates long before its battery dies. We are told this is normal part of the price of living in a fast, innovative age. Yet scattered across deserts, coasts, and cathedral towns are structures built with hand tools and flame that still stand, still work, still astonish. The contradiction is not subtle. It is a neon sign, flickering in daylight. Modern life worships speed, not longevity, novelty, not memory. We've mistaken fast change for real progress. This opening chapter is not a nostalgia trip. It is a clear-eyed look at how a civilization's assumptions shape what it builds. The story you are about to follow is anchored in a simple claim. Progress is not a straight line with us at its peak. It bends, loops, forgets, rediscovers. Some technologies improve, others quietly degrade under the pressure of profit, fashion, and short-term thinking. The past we casually call primitive often concealed deeper mastery of materials, of forces, of limits that we would do well to learn again. Modern life runs on replacement. Shoes delaminate on schedule, appliances are riveted shut, software sunsets make perfectly functional hardware obsolete. The term for this is planned obsolescence, designing products to fail, to be unrepairable, or to be socially unfashionable on a predictable timetable. It is not a conspiracy theory, it is a business model. It turns the everyday world into a subscription service for physical things, with our wallets underwriting the churn. Older cultures, by necessity, optimized for a different metric, endurance. They could not afford a civilization of throwaways. Material was expensive, energy was muscle and wind, and knowledge was hard-won. So they built in conversation with time. In that conversation, the Romans asked their coasts and quarries how to pour stone that would heal itself. Medieval millwrights listened to rivers and found gears that multiplied flow into work. Cathedral builders negotiated with gravity until stone learned to fly. These were not hacks pasted onto brittle systems. They were systems designed for stability first, flexibility second, spectacle last. When you examine what endures, you begin to see an ethic. Durable things are rarely the cheapest short term. They demand care up front, accurate joinery, well-chosen aggregates, realistic loads, patient curing times, redundant supports. They reward that care with decades or centuries of service. The medieval world did not always meet this standard. Shoddy work existed then too. But its best work was made in a different economic climate, one where failure could not be shrugged off with a warranty slip and a landfill. This chapter is a map of where we are going. We will test the modern myth that more recent equals better by visiting 12 families of ancient and medieval know-how. Each illuminates a piece of a larger thesis, that many pre-modern systems embedded durability, repairability, and environmental fit as design goals, not afterthoughts. We begin with material science that should embarrass us. Roman seawalls and piers cast from a slurry of lime, volcanic ash, and rock do something our standard concretes do not. They get stronger in the presence of salt water. Cracks activate chemistry, minerals precipitate. The structure partially self-heals. It isn't magic, it's intelligent composition tied to use and environment. They didn't have finite element software. They had failure, observation, and iteration over generations. From stone and salt we shift to sand and friction. In Egyptian murals, a worker pours liquid in front of a sledge hauling a colossal block. For centuries people assumed this was ritual. It turns out to be physics. The right moisture content stiffens sand and halves the force required to drag. The image is more than a footnote. It is a window into a mindset. They were not just fighting the desert, they were engineering it. Energy comes next, long before steam and coal. Watermills and windmills are not quaint. They are automated labor off-grid, self-regulating, sized to local flow and gusts, with gearing that converts chaos into useful, repeatable motion. A valley that acquires mills, acquires manufacturing, grain, textiles, metalwork. The medieval version of scaling did not require wires. It required good sighting, stout timbers, careful teeth on wheels, and a miller who understood the seasonal moods of water and wind. Sometimes the evidence is missing not because the technology was mythic, but because it was valuable. If you build a lifting machine from timber and rope to raise stones inside a monument, you take it apart when the job is done. You reuse every component. The blueprint is memory in the hands of craftspeople. When those hands are gone, the device is a rumor in a text. We will read those rumors with the charity due to societies that left their tools in place only when they were useless. War, regrettably, is often a forcing function for innovation. Greek fire, a naval flamethrower long before gasoline engines, combined chemistry with pressure systems precise enough to terrify fleets. The counterweight trebuchet harnessed gravity with a sophistication that cheapens the word catapult. These were not acts of desperation, they were clear thinking under constraint, designed for repeatability and control in chaotic conditions. Then there is the cathedral, a thesis in stone. Pointed arches that steer forces downward, ribbed vaults that lighten and strengthen, flying buttresses that carry lateral thrust around windows instead of through them. It is a structural system, not a style, and it is shockingly efficient with material. Where Roman interiors needed mass, Gothic interiors used geometry. If you have ever walked into such a space and felt the invisible math that holds it aloft, you already understand why this series treats medieval engineering as a live lecture in physics. Within those walls, light becomes engineering too. The rose window is not a hole decorated with glass. It is a load-bearing diagram, a stone computer that routes compressive forces along carved paths while shaping color and luminosity to orchestrate space. Its survival through fire and war is not lucky. It is the predictable outcome of redundancies carved by people who accepted that time would test their work without mercy. The gears of medieval timekeeping and the brass plates of the Astrolabe complete the arc from matter to mind. An escapement turns falling weights into ticks. Ticks turn into hours mapped to bells. Bells regiment daily life into a cadence that makes industry possible. An astrolabe turns the sky into a pocket interface for navigation, surveying, and prayer times. These are not gadgets. They are instruments, tools that expand human agency by compressing complex relationships into graspable forms. At this point, the critique of modernity practically writes itself, but let's be specific. What did many pre-modern systems do that we often do not? First, they fit their environment. Mills were sized to rivers, not rivers forced to feed mills. Materials were local, not shipped across oceans to match a color palette in a brochure. Construction recipes, adapted by region, because the ground and weather demanded it. Second, they anticipated failure. Stone ribs and redundant arches are not overkill. They are humility made visible acceptance that wind, snow, and time will hunt for the weak point. To respect that hunt is to build escape routes for forces before disaster draws its own. Third, they invited repair. Pegged joints, accessible mechanisms, parts made from standardized timber sizes or stock plates. These choices put maintenance within the reach of local skill. We replace entire assemblies today because the fastener is proprietary and the service manual is a trade secret. Fourth, they aligned with human learning. When your watermill breaks, the miller listens, feels, smells. The diagnostics are in the senses, not locked behind error codes. Knowledge accumulates in apprenticeships and in the wood itself. Grooves where pressure lives. The system teaches you where it wants attention. To praise these virtues is not to deny medieval squalor, violence, or superstition. We do not want to swap antibiotics for leeches, but we should resist the lazy reflex that the past holds nothing technical to teach us. The truth is pointed. Durability, repairability, and ecological fit are not luxuries. They are skills. Skills can be taught, practiced, lost, and relearned. If you want a test of a culture's seriousness, ask how it treats time. Do we design products to serve people for as long as possible, or do we design people to serve products for as long as profitable? The answer is written in landfills, in software locks, in buildings that age like fruit. And it is written too in bridges that shrug off centuries, in windows that turn sunlight into theology, in machines that hum without wires. This series is a guided tour of that second script, the one where human beings worked with gravity and grit to embed wisdom into matter. Not everything old is good, not everything new is bad, but some old things are better because they were forged under constraints that demanded honesty, limited energy, costly error, slow supply lines, communal memory. We, facing climate strain and material limits of our own, are drifting back into a world where those constraints will again be non-negotiable. The medieval lesson isn't romance, it's relevance. So we start by clearing the fog from a single idea: modern equals superior. Sometimes it does, often it doesn't. The real question is not whether an age is advanced, it is whether its artifacts honor their users, their place, and their future. Rome poured concrete to greet waves. 1,000 years hence, millwrights tuned teeth to the moods of spring melt. Masons drew circles that held while kings fell. If that is primitive, then perhaps our definitions need repair. Keep this lens handy. In the chapters ahead, we will examine how specific pre-modern systems, beginning with a certain Roman recipe of stone, ash, and sea, were engineered to collaborate with time itself, and how relearning that collaboration can change the way we build today. Stand on a Roman pier, and you're standing on a chemical engine that has been quietly running for 2,000 years. Storm after storm rakes the coast. Waves grind, salt invades, ice wedges, sun bakes, yet the mass below your feet does not surrender. Modern concrete, left to the same onslaught, flakes and spalls like pastry. Roman concrete does something impolite in the presence of seawater. It gets better. The Romans did not invent the idea of binding stones with paste, but they transformed it from a crude mud into a calibrated geology in a box opus caementicium, a cast stone poured to perform. Their recipe seems simple when you list it. Lime, the reactive heart, volcanic ash, the siliceous brain, and aggregate, the skeleton. Simplicity is a magician's trick. What matters is which lime, which ash, which stones, and how they are combined, placed, and cured in the world. That is where genius lives. Begin with the ash. Romans called it pulvis or pozzolana. From the deposits near Pozzuoli in the Phlegraean fields west of Naples, ash born of roaring geology, saturated with amorphous silica and alumina. Mix that with lime and water, and you don't just make glue, you trigger a slow, stubborn pozzolanic reaction that forms needle-like crystals and calcium-aluminum silicate hydrates, minerals with names like tobermorite and stretlingite. In modern mixes, those phases are rare and fragile. In Roman marine concrete, they grow thick and interlocking over time, stitching microcracks, armoring pores, and turning the interface with seawater into a zone of self-defense. Now, the lime. Modern builders usually slake quicklime into a smooth putty before mixing, aiming for homogeneity. The Romans often practiced hot mixing, combining quicklime directly with damp ash so that exothermic heat surged through the mass. The result was not a creamy uniformity, but a landscape of texture. Regions fully reacted side by side, with lime clasts, stubborn white nodules of partially reacted quicklime. To the modern eye, that looks like poor quality control. To the sea, it is a network of sleeper agents. When a crack opens and water invades, those clasts wake up, dissolve, and reprecipitate crystals in the wound. The concrete becomes its own repair crew. Aggregate. Here the Romans refused one-size-fits-all. Piers and breakwaters demanded dense, tough rubble tufts and lavas that matched the chemistry of the binder. The Pantheon's soaring dome wanted the opposite lightness, so they graded aggregates up the height, from heavy basalt in the base to pumice near the crown, tuning density the way a luthier tunes a string. They even varied the ash. A mix for a harbour was not a mix for a vault. Each formula was a contract with the forces it would face. Placement. Roman harbour concrete was often cast underwater. Crews lowered wooden formwork cofferdams into the surf, then tipped in layered charges of rubble and hot mixed mortar in a slurry called fabrica. Sea water was a partner, not a contaminant. It seeded chloride and sulfate ions that would normally corrode steel and shred modern matrices. But there was no steel to rust, and the matrix wasn't modern. In that alkaline bath, pozzolanic reactions meandered for decades, trading early strength for an astonishing long game. Modern concrete, by contrast, is a sprint. Portland cement hydrates fast, gains impressive early strength, and then spends the rest of its life fending off its own weaknesses. Microcracking from thermal swings, alkali-silica reactions between paste and aggregate, carbonation, chloride ingress. We lace it with steel to carry tension, and the steel becomes a Trojan horse marvelous until oxygen and salt reach it, at which point rust swells like a wedge. Our structures are strong, young, and fragile old. Roman concrete is the opposite, modest early, imperturbable after. It is tempting to romanticize, to say they knew secrets we do not. That flatters no one. What they had was a culture of fit, of tailoring material to place, and a willingness to let time finish the work. Pozzolanic reactions do not hurry because a schedule says so. They cure as they cure. A Roman engineer accepted that the sea would be the final kiln. Consider a case study: a breakwater on the Tyrrhenian coast, built in an era when emperors still strode marble. Drill cores reveal microstructures that would make a materials scientist grin. Jumbled fragments of tuff, locked in a matrix, peppered with lime clasts and pozzolanic gels. Veins of crystalline tobermorite, traversing old cracks like bone knits. The ocean hasn't just failed to destroy the concrete, it has educated it. Every winter, brine penetrates microfissures, and the chemistry adjusts, crystallizing more intergrowths, refining pores, lowering permeability. The breakwater is a living archive of storms. Longevity wasn't an accident. It was logistics. Romans quarried aggregates near the work, ferried ash by barge along known routes, burned lime from local limestones, whose impurities subtly tuned reactivity. The supply chain was regional, not global. Quality control was embodied in people, architecti, and fabri, who learned by apprenticeship, corrected by failure, and handed down rules of thumb that sound like poetry until you realize they encode humidity, heat, and season. Mix when the air drinks the sea is not mysticism, it's a schedule written by weather. Isn't this just because they didn't use steel? Partly. Remove steel and you remove a path to catastrophic corrosion. But that does not explain the whole difference. Plenty of unreinforced modern concretes crumble under freeze-thaw or sulfate attack. The Roman binder itself is chemically different, not merely steel-free. Its microstructure evolves in the presence of brine toward minerals that our standard mixes struggle to grow, because Portland chemistry, optimized for speed, takes another path through the mineral garden. What about compressive and tensile capacity? Roman concrete is superb in compression and abysmal in tension, just like ours. The Romans adapted by designing for compression. Arches, vaults, domes, mass, and geometry that usher forces into compressive paths. Where tension threatened, they used bronze clamps or timber ties, but sparingly. The lesson isn't to abandon reinforcement. Steel and pre-stress made bridges possible that Romans could not dream of. The lesson is to align form with material, to ask what a substance wants to do, and draw structures that cooperate rather than constantly fight. Carbon, the quiet accountant, has an opinion too. Portland cement is a carbon bully. Calcining limestone and fueling kilns spew CO2. Pozzolanic cements replace a portion of Portland with industrial byproducts like fly ash or slag to soften the blow. But those supply streams are shrinking, and their chemistry varies. Roman-like binders point a different way: more lime, less clinkered phase, reactive volcanic materials that cure slower but last longer. Over a building's life cycle, durability is carbon mitigation. The greenest replacement is the one you never pour because the old work still stands. Could we just copy their recipe? The honest answer, sometimes. In volcanic regions, yes, engineers already use natural pozzolans, blended with lime and cement, to reach high durability in marine or sulfate-rich soils. Hot mixing with quicklime and purposeful limeclasts is being reconsidered for specific applications where self-healing is valuable and early strength demands are modest. But translation is not photocopy. Modern codes, construction schedules, labor practices, and expectations differ. If your client wants a parking garage opened in 6 weeks, Roman kinetics will not oblige. So the point is not cosplay, it is principle. Choose binders that continue to react benignly with the environment they face. Accept slower early strength when life cycle performance demands it. Use aggregates and admixtures that work with the binder, not merely fill space. Design forms that keep forces compressive where the material is happiest. Remove or protect the elements most vulnerable to the environment you cannot change. There is also a social technology embedded here. Patience. Roman concrete took time to gather, time to mix, time to cast, and time to become itself. That patience is not nice to have, it is part of the mechanism. We can accelerate everything with plasticizers and steam curing, and sometimes we must. But we should name the trade. You eat into the margin that time would have given you later. If the sea is the Roman teacher, earthquakes are the exam. Many ancient Roman concrete structures in seismic zones have fared impressively. Mass helps, but so does jointed construction courses, belts, and interlocks that allow distributed cracking rather than sudden failure. Even in ruin, you can see the intention. A wall that holds enough mass in enough places that a shock becomes damage, not collapse. Again, the ethic shows itself. Act as though the worst will come, and carve into the form the routes for energy to go when it does. Walk the port of Cosa, or the stumps of piers at Caesarea, or the great drum of the Pantheon, and the modern mind performs a double take. We imagine ourselves the adults of history, and these, at best, the precocious children. Yet, here is a body of work that treats adversity as collaborator, chemistry as ally, geometry as etiquette, and time as co-author. It is hard not to feel the gentle rebuke, build with the world, or the world will unbuild you. There is an elegant cruelty to the comparison. We call in consultants to patch 3-decade-old parking structures. Romans poured concrete that meets us now with a faint smile. Still here, the challenge is not to fetishize ash and lime, but to recover a design attitude that binds materials, environment, and use into a pact. The Romans wrote their pact in volcanic glass and burned stone. We can write ours in supplementary cementitious blends, calcined clays, low clinker cements, non-corroding reinforcement, and forms that make tension earn its keep. In the chapters ahead, you'll see this ethic repeat in wood, wind, water, and light. For now, carry forward one stubborn fact. Roman concrete is not a relic, it is a reminder. It reminds us that the difference between lasts a lifetime and lasts a civilization is not a miracle material waiting to be discovered. It is thoughtful composition, honest geometry, regional logistics, and patience disciplines that any age can practice, if it chooses to build for the people who are not yet born. Picture a line of workers in the morning glare of the desert, a wooden sledge groaning under a block the size of a room. One man walks ahead with a jar and pours water onto the sand. For a long time, scholars filed that scene under ritual. Surely he is blessing the work, anointing the path. Then physics spoke. The image painted in the tomb of Jehuti-Hotep, nearly 4,000 years ago, records a practical insight of startling elegance. Tune the sand, and you tame the desert. What does water do to sand? In a child's bucket, it makes castles possible. In the mechanics lab, the reason is capillary bridges, tiny liquid necks that form between grains and glue them into a semi-cohesive mass. Dry sand behaves like marbles, saturated sand turns to mush, but at the right moisture content, grains interlock and resist shear, in a way that bears load and yields a smooth, firm track. When a sledge runner slides over that tuned surface, required pulling force can drop dramatically. Experimental studies suggest by as much as half under ideal conditions. That is not a marginal gain. It is the difference between barely moving and moving well. Friction is not a single number. It is a relationship between surfaces that changes with texture, pressure, speed, and environment. The Egyptians did not write equations for it. They felt them, and then they engineered. Consider the sledge. A simple plank will gouge and stall. But give the runner a gentle curvature at the front, polish its underside, and you distribute pressure while encouraging the sand to compact, not dig. Now add a film water, and at times animal fat or oil where wood meets ground. You have, in essence, a primitive tribology lab in the open air. Solid, granular, liquid interactions, tuned by craft, until the machine of people plus sledge plus earth becomes one organism. The choreography matters as much as the chemistry. A hauling team that yanks in ragged bursts wastes energy in start-stop cycles and lateral snaking. A team that moves in cadence minimizes dynamic losses. Drums, chants, and call and response are not mere morale. They synchronize force so that micro stalls do not cascade into macro failure. The overseer's job is less whip than metronome keeping phase between dozens of human engines, so the vector sum of their effort stays aligned with motion. We have a tendency to imagine ancient projects as brute force applied to brute material, but to pull a multi-ton block across kilometers of desert requires an ecosystem of optimizations that reach from quarry to monument. Timing the move for the cool of morning reduces thermal softening of wood and lowers heat stress on workers. Storing water along the route transforms moisture from scarce resource into infrastructure, meted out not for thirst alone, but for ground preparation. Ropes, likely plant fiber like papyrus or palm, must be pre-stretched and inspected, so that load sharing between strands is even. A single weak line increases shock loads on the rest. Wooden rollers might come into play over particularly soft soil, but they, too, must be staged and retrieved without introducing chaos at the handoff. What looks like a single technique, pour water ahead, is in practice a control loop. Too dry, drag spikes, the sledge jerks, ropes bite. Too wet, the surface liquefies, and the runners plow. The man with the jar is not sprinkling, he is calibrating, watching the imprint of the runner, the gloss of the sand, the immediate change in sound and feel. He is a sensor and actuator in one. Every few meters, the team reads the road again. The sledge itself is not a monolith. Its construction encodes lessons hidden to casual eyes. Hardwood where wear is highest, softwood in the body to save weight, dowel joints that can be knocked apart for repair. Iron is rare and costly, so pegged joinery dominates. A rope harness attaches low to the sledge to reduce pitching moments. Crossbars for pullers are set to keep shoulders aligned with direction of motion, minimizing sideways shear on the sand. When the load is extreme, a pilot sledge can pre-compact and pre-wet the path, turning the main haul into a smoother glide. Scale this up and you get logistics by physics. Quarry ramps are built not with the steepest climb, but with the longest constant grade the crew can sustain without dangerous backward slips. Where the terrain demands turns, switchbacks widen corners so that the sledge does not climb its own outer runner and tip. At staging areas, blocks rest on cribbing, the simple genius of crossed timbers that make it easy to insert levers underneath and relaunch. The crane is not yet in the picture, the lever is, and so is the counterweight. Men on one side, stones on the other, trading height for force with mechanical grace. It is often said that if you have enough time and slaves, you can do anything. That is a lazy thought that erases the intelligence of people whose lives depended on getting the physics right. Time and bodies alone will not move 100 tons up a narrow ramp without catastrophic losses. You need reliability processes that reduce variance. Tuning sand moisture is a variance killer. So, are well-maintained runners, the right cadence, clear signals, and route preparation that anticipates hazards instead of discovering them by accident. Let us be explicit about what this is and is not. It is not evidence of sonic levitation or lost alien cranes. It is evidence of iterative experimentation measured in scraped knuckles and small triumphs. Try dry, fail. Try soaked, fail differently. Try damp, succeed, then tune. In modern terms, the Egyptians ran A/B tests with human feedback and kept the version that made a hard problem tractable. Their understanding extended beyond horizontal hauling. When blocks needed raising, they applied the same attitude. Reduce friction when sliding is desired. Increase it where holding is essential. Earthen ramps get sprinkled and trampled to a crust. Hallways are kept smooth and free of debris. Stopping points are roughened or chocked so the load wants to rest there. The line between disaster and success is thin enough that every detail counts, which is another way of saying that system thinking is ancient. Why does this matter to us? Because the frontier of engineering is not always new materials or exotic machines. Sometimes it is learning to engineer environments to make the medium through which you move work with you. That principle reappears wherever we move heavy things through unfriendly terrain. Laying geotextiles under gravel to stabilize soils, pre-compacting roadbeds, spraying water on mine-haul roads to reduce dust and rolling resistance, even using humidity control in factories so that paper and textiles behave. We also inherit the social side of the lesson. When labor is seen only as cost, you drift toward systems that burn people out and then replace them. When labor is seen as part of the mechanism, you design for human performance. Shade, cadence, predictable loads, clear lines of responsibility, tools that communicate their state through sound and feel. That Egyptian hauling line is not just muscle, it is organization, roles, signals, feedback, iterative improvement. There is a humility here worth carrying forward. The Egyptians did not pretend the desert would change for them. They learned its moods and edited it at the margins, moisture here, compaction there, until the desert became, briefly, a partner. The gains are small in any single step. Over miles, they accumulate into the difference between a plausible monument and an impossible dream. The painting of Jehuti-Hotep is therefore not quaint. It is a diagram of applied common sense, elevated into craft. It shows a civilization that, lacking engines, built engines out of relationships, wood to sand, water to grains, lungs to rhythm, rope to teamwork. If we strip away the romance and keep the method, we find a principle hiding in plain sight. Engineer the interface, and the rest will follow. In the next chapter, we will watch water itself become the engine, no longer an environmental parameter to tweak, but a prime mover harnessed in mills and gears. The logic does not change. Listen to the medium, shape it until it cooperates. Then, let it work while you rest. Before pistons and wires, power came from backs and bellies. A civilization's horsepower was literally horses, plus oxen, plus the human pulse. Then, somebody looked at a river and realized, this is a patient animal that never sleeps. If you can persuade it to push a wheel, it will grind grain while you dream. That moment when we yoked moving water to rotating wood is the quiet birth of automation. A watermill is simple in story and profound in detail. A stream is diverted into a leat, a man-made channel that carries water at a chosen height. A gate releases that flow onto a wheel. The wheel turns a pit wheel, a large horizontal gear, which bites a smaller vertical gear called the wallower on an upright shaft. Up top, that shaft spins a great spur wheel, whose wooden teeth drive lantern pinions connected to millstones. It reads like a children's toy, but every step is an argument with physics. Maximize torque at low rotational speed, convert direction without crushing teeth, keep everything aligned despite timbers swelling with humidity. It's a doctorate in wood. Not all wheels are equal. An undershot wheel stands in the current. The river pushes its paddles directly. It's simple, cheap, and unimpressed by drought because it needs only flow, not height. But it is also inefficient. Water hammers the paddles and slips past without giving up much energy. An overshot wheel, by contrast, takes water at the top via a launder. Each bucket fills, and gravity pulls the mass down. The water drains at the bottom. Efficiency climbs, because you capture head height as well as flow. In between lives, the breastshot wheel water strikes near mid-height, and then rides down in partly filled buckets, a good compromise for modest heads and sturdy rivers. The Romans knew all this in bones and timbers. The complex at Barbegal, in what is now southern France, stacked 16 water wheels in 2 parallel cascades down a hillside. Imagine it as a terraced factory, water dropping from one wheel's tail race into the next wheel's head race. Power handed down like a relay baton. Grain went in at the top. Flour came out below industrial throughput without a single boiler. When we say factory, we usually picture brick, steam, and a whistle. But here, in the 2nd century, is an automated plant with a supply chain, quality control, stone dressing for uniform flour, and maintenance schedules replace paddles, true-up shafts, adjust gates. It is not quaint. It is scalable. The medieval world made mills common. Monasteries cited them as revenue engines. Lords claimed banal rights, obliging peasants to grind grain at the lord's mill for a fee. That sounds feudal because it is, but it also shows how deeply mills embedded into everyday survival. A pair of hand querns can feed a family. A watermill can feed a town and free hands for everything else. Masonry, weaving, metalwork, letters. Automation is not only about labor saved, it is attention liberated. Inside a well-run mill, the soundscape is a user interface. The rumble of the stones, the hiss of grain in the hopper, the creak of timber frames, the slap of the belt on the damsel, the little rod that jiggles grain into the eye of the upper stone. Each sound carries state. A miller can hear when stones are too close. They cry when the dressing has dulled, when the leat is starved, when a tooth has split. Maintenance is listening made useful. The machine tells you how to keep it alive. Numbers? A healthy overshot wheel of a few meters diameter might deliver a few kilowatts, enough to drive millstones, hammers, bellows, or saws. One mill equals dozens of laborers, tirelessly, multiply across rivers, and you get a distributed grid, each node tuned to local hydrology. There is carbon in this story, as in, very little. The energy arrives by gravity and weather, not by burning. Infrastructure is wood, stone, and iron widgets, where strictly necessary. When mills fail, they fail slowly. When they succeed, they rack up centuries. But water has moods, and so millwrights became psychologists. Spring floods will tear a wheel to pieces if headgates and sluices aren't sized and sighted with caution. In winter, ice turns launders into brittle sculpture. In summer, low flow demands gates that meter dribbles efficiently. Millwrights learn to use trash racks to keep branches out, to set tail races that don't drown the wheel, to scribe trunnels, wooden dowels that hold joints but can be replaced before a split becomes a collapse. Every river is a personality. Every mill is a biography of that relationship. When rivers failed or terrain denied easy head, people looked up. The wind had always been a nuisance. Now it became a collaborator. The earliest recorded vertical axis windmills, think of a giant rotating door of sails, appear in Persian lands, shaped by dry winds and scarce water. The aerodynamics are crude by modern standards, yet they work because the sails present drag to the wind on one side and shelter on the other, yielding net torque. Simple, robust, apt for desert towns where a stream is a rumour. Northern Europe invented a different creature, the post mill. The entire mill body sits on a single massive post and can be swung to face the wind. Here, we trade vertical axis drag for horizontal axis lift, the same physics that will one day keep airplanes aloft. Sails cloth, stretched on wooden frames, catch wind with adjustable angle. The machinery inside echoes the watermill in spirit. Large, horizontal gear to vertical wallower, to upright shaft to stones. But now the prime mover is capricious. The solution? Human in the loop control. Reef the sails when gusts threaten to overspeed the stones. Feather them when the breeze weakens. Turn the mill to stay head to wind. Later, the tower mill fixes the body in masonry and lets only the cap rotate, stouter and safer. Later still, a fantail, a small wind-driven vane, automates the yaw so the mill noses into the breeze by itself. That is, control theory, in shingles and iron. The beauty of wind power is its geographic democracy. A village on a ridge can grind grain without leasing water. A coast can pump brine or drain marsh with scoop wheels. A polder in the Low Countries becomes land because a constellation of mills breathes water out of it day and night. Each mill is modest. Together, they are a civilization shaper. Ask yourself which is more modern, a single huge machine feeding a continent through wires, or thousands of local machines fed by the weather they live in. The answer is not moral, it is strategic. The medieval system is resilient by distribution. There is an intellectual step here as important as any gear. Water and wind are not just fuel, they are timekeepers. A mill's cadence sets working day and market day, bakes towns into weekly rhythm, and tutors communities in seasonality. To live with a river is to remember spring flood and autumn lean, to schedule repair when fish run or fields demand hands. That memory becomes policy, laws about weirs and rights of way, customs about who may draw from the leat and when. Engineering spills into governance, because the resource is shared and the machine is public. If the mill is a prime mover, it is also a platform. Swap stones for cams and trip hammers, and you can drive a forge. Bellows feed a charcoal fire, while water lifts hammers to pound blooms of iron. Add cranks and saw blades, and you have a sawmill. Timber becomes plank, with a steady mechanical scream that once only forests heard. Feed a tilt hammer with wind and water, and you prefigure the factory floor, a choreography of repetitive motion, powered by landscape. The critique writes itself. Rivers silt, mills flood, droughts idle wheels, sails rot, gusts maim. This is not a utopia of frictionless sustainability. It is an honest one. Failure modes are visible and local. Repair is plausible and mostly low-tech. When a paddle breaks, a carpenter can fashion a new one. When a launder leaks, pitch and patience fix it. And when climate swings, the mill reminds the village in tangible form, not in an abstract chart. Why does this chapter sit in a story about medieval genius? Because water and windmills are embodied theory. They show that you can multiply human strength without fossil fuel, that you can encode knowledge in wood such that a teenager, apprenticed to a miller, inherits centuries of debugging. They are, in our terms, edge computing, decision-making and action, close to the source of data, the river, the gust without a distant command center. They scale by copying patterns, not by centralizing. We can, if we wish, be literal about bringing them back. Microhydro and small wind already dot hills and creeks, feeding microgrids and workshops. But even if your city will never grind flour on a water wheel again, the pattern language survives. Tune machines to local flows, design for maintenance by the people who live with them. Use redundancy to ride the moods of nature, instead of bullying them with over-specification. Soon we will re-enter stone chambers and rumors to ask how ancient builders lifted and set weights that still puzzle us, machines made of short wooden planks, as Herodotus put it, now vanished, because their wood returned to other uses. Keep today's lesson in your pocket as we go. Energy is everywhere if you learn to speak to it. Rivers speak in head and flow, winds in gust and lull. The millwright's grammar, gears, gates, sails, Stones is simply how you answer back. Herodotus drops the line like a breadcrumb in a maze. The Egyptians, he says, used machines made of short wooden planks to lift stones, raising each block from one tier to the next. And then, nothing. No diagram, no exploded view, no material list. Just that maddening phrase, suspended between reportage and rumor. For 2 millennia, the sentence has baited builders and dazzled mystics. What were these machines? Ramps, cradles, counterweights? The sensible answer is both modest and thrilling. They were clever wooden devices, modular, portable, replaceable, that multiplied human effort with leverage and gravity, then vanished because people took them apart and turned them back into wood. Start with constraint. Egypt is rich in stone and poor in timber. Any lifting system had to be parsimonious with wood, quick to assemble, easy to repair, and light enough to move up a growing monument. It also had to be repeatable. You do not build a pyramid by inventing something new at every course. You standardize a small kit that crews can use in parallel across faces, corners, and interior passages like a factory without walls. Now, think like a carpenter. Short planks suggests cribbing and levers, not colossal frames. Imagine U-shaped wooden cradles that hug a block, pinned with pegs through mortises so the stone cannot slip. Under the cradle, a track of timbers dressed smooth and waxed or greased with animal fat. On either side, shears A-frames lashed at the top, carrying a rope over a wooden roller. Pull on the rope, the cradle climbs a few inches. Chocks are kicked under it. The rope is reset. The cradle climbs again. It's a ratchet made of wood and willpower. Multiply the stations, and a block ascends the face in stepwise fashion like a centipede walking up a wall. Or picture a counterweight sled in a covered slot. The grand gallery of the Great Pyramid has seduced many into this thought. The gallery's corbelled sides and series of mysterious rectangular cutouts could have anchored a guiding track, while a heavy sand-filled box ran up and down, trading altitude for force through ropes over beams. The model is a shaduf, the farmer's seesaw crane scaled and reimagined indoors. Does the evidence make this certain? No. But the geometry whispers possibilities. Narrow passage, great height, provisions for beams, scars from repeated loading. When you lack drawings, you listen to stone. Less glamorous, but just as likely, is a terraced ramp hugged tight to the monument. Not the cartoonishly long causeway devouring half the Nile Valley. Horizontal ledges wrap each tier. Blocks are hauled along a ledge to a corner, turned, then levered up to the next ledge, a choreography of short moves and small lifts. Where the ledge turns are tight, blocks are slewed, nudged around by alternating pry points and chocks. In soft light, you can almost see the rhythm: pull, wedge, breathe, pry, chock, breathe, reset, repeat. Wooden rollers? Possibly, but over sand they tend to plough unless the surface is prepared. Recall our tuned damp sand from Part 3. More likely for short repositioning on platforms than long hauls. Ropes? Absolutely. Fat, twisted from palm or papyrus, pre-stretched to avoid surprise slack, inspected daily for broken fibers, retired before catastrophic snap. Rope is a machine in itself, and its archaeology survives as grooves worn into stone where lines bit and slid. The best evidence for lost wooden devices is in the wear patterns and logistics that stone still records. At quarries, you find severing trenches and V-notches where teams drove wedges to pop blocks from bedrock. You find drag marks that curve toward ramps and staging areas. At sites, you find bosses' small nubs left on block faces to grab with tongs or to anchor levers later dressed away when no longer needed. You find sockets in floors that once accepted posts and patches where posts crushed stone. You find standardization, block sizes that match a known carrying capacity for a 4 or 6 man team with a sledge, multiplied across dozens of teams working in parallel. You find bakeries and barracks, the worker villages whose bread and beer are as crucial to lifting as any rope. We also have experimental archaeology, the stubborn craft of trying things with sweat and timber, Build a short crib ramp. Haul a 2-ton block up it with a dozen people. Log the failure modes. You learn fast. A lever snaps where the grain runs across a knot. Next time your foreman selects straighter stock. A sledge bites a groove and stalls. Next time you radius the runner and damp the path. The block slews dangerously at a corner. Next time you add a pilot sledge to prepare the turn, or you staple wedges to guide the nose. The hypothesis evolves until, one afternoon, the crew looks at the stone, standing a course higher, and shrugs. Of course, it works. The past is now obvious, because your shoulders remember it. Why don't we find the machines? Because wood is valuable. When the last casing stone is tapped into place, every trestle, cradle, sledge, roller, and A-frame becomes raw material for roofs, boats, coffins, furniture, fuel. Metal fittings, if any, are pried off and reforged. What remains is what had to remain: holes in the floor where a post once stood, smooth scars where a beam fretted, geometry that still fits a beam of a likely size. We should put to bed the idea that lost equals mystical. The Egyptians did not need exotic physics to lift stones. They needed error budgets and risk management. A project this large survives by constraining variability, consistent block dimensions, predictable friction, ramps of steady grade, procedures for corners, hand signals for starts and stops. Stop rules when rope fibers fray or heat overcomes people. In other words, process the most powerful technology we have. But the devices were not only ramps and levers. Consider tilting. A block on a sledge can be rocked so that one end rises while the other serves as a pivot. A spacer is kicked under. The operation repeats at the opposite end. You've walked the stone up several inches without hauling it the long way around. Consider stone ladders, stepped cribbing, whose heights match a pry bar's comfortable stroke. Consider sledge shoes, replaceable hardwood runners, pegged to the sledge that can be swapped when worn, preserving the expensive body. Consider countersands, bags of sand used as tunable counterweights. As the block rises on a lever, sand leaks from a bag hanging on the other arm, smoothing the motion like a primitive hydraulic damper. None of this requires iron. It requires understanding where wood is strong in compression along the grain, and how ropes talk with harmonics that warn of impending failure. And then there is coordination. The worker city at Hayt el Gharab near Giza shows organized crews with names, rations, and pride. Crews that share meals share timing. Crews with reputations share standards. The machines of short planks include these human machines teams trained to become predictable actuators. A lifting system often fails not at the lever, but at the handoff between teams, where nobody is quite in charge of the next wedge. Rituals, songs, shouted counts, drumbeats become safety systems. The technology is social. What about the internal ramp thesis, the idea that blocks climbed inside the structure? It has elegance. Spiral corridors protect the work from crosswinds, shorten exposure, and make theft of timber harder. It also has problems. Corners are tight, and turning big pieces inside a maze is a choreography of inches. Yet we should allow that different monuments likely used different blends. External ramps early, internal corridors later, big blocks levered, smaller ones hauled, local geology and available timber dictating the mix. The point of this chapter is not to pick a single silver bullet. It is to recover a way of seeing. When timber is scarce and stone is cheap, you invest thought in wood and let stone be your ballast. When labor is precious because people are not expendable, you replace brute force with repeatable physics. When records are sparse, you let scars, sockets, and statistics be your documents. Lost, in this sense, means absorbed by usefulness. The machines disappeared because they succeeded, not because they never existed. There is a cultural lesson tucked here, like a wedge under a block. Technologies that are modular, low status, and wooden tend to be forgotten first. We enshrine bronze statues and marble inscriptions. We burn scaffolds and trestles. But scaffolds and trestles are where the intelligence lives, the applied geometry that turns an idea into a wall. If we want to remember more honestly, We must honor the temporary apparatus as much as the permanent result. In the next part, the wood stays, but fire joins the cast. We'll watch Byzantines pressure feed terror across the sea, and medieval engineers drop stones on walls with a precision cannon could envy. Gravity will become fuel. Chemistry will become theatre. The lesson persists. Empty hands, short planks, long thought. War has a way of forcing clarity. You either move stone and flame with intelligence, or you bury your dead beneath your own mistakes. In the long centuries before gunpowder remade siege and sea, two technologies stood out for their unnerving elegance: a liquid that burned on water, and a gravity engine that could unpeel castle walls. Greek fire and the counterweight trebuchet are not just medieval party tricks. They are masterclasses in controlled energy pressure, leverage, timing staged in wood, bronze, leather, and nerve. Start with the sea. Picture a Byzantine dromon, a long, low warship with ranks of oars chewing the water near Constantinople's sea walls. On her foredeck sits a bronze beast, a siphon with a lion-headed nozzle. Behind it, a hand-pumped pressure system. Pistons, leather seals, check valves that turn human muscle into a steadied stream. In the belly are sealed containers of a foul, viscous mixture whose exact recipe died with the city in 1453. We can infer likely ingredients: petroleum distillates drawn from seep and still, quicklime to heat and tighten, sulfur for stick and stink, resin for clinging. Whatever the proportions, the effect is simple and terrible. When the ship closes range and the pump team leans into their strokes, a rope tug from the officer opens the firing valve and the lion spits a sheet of fire. Not a tossed pot or a fragile jar, but a directed jet that clings to wet wood and skin, roaring. The genius here is not only chemistry, it's hydraulics. A flamethrower without pressure is theatre. With pressure, it becomes geometry. Range and arc tuned by nozzle diameter, stream coherence tuned by pulsing the pumps in rhythm. The crew's muscle becomes a waveform. The device turns that waveform into distance and coverage. You can rig smaller, portable siphons to mount on walls, swivel them on gimbals, aim down into the clutter of ships at a boom chain. You can even load fire pots, ceramic grenades, filled with the stuff, into catapults for indirect arcs. But it is the pressure-fed stream that haunts adversaries, because it breaks the rules. Fire should die on water. Here, it thrives. Greek fire also teaches risk management. A ship carrying volatile tanks and a hot pump crew is a hazard to friend as much as foe if discipline slips. So Byzantines wrap the technology in ritual and secrecy. Specialist units, oaths of silence, single-family custody of recipes, carefully staged deployment only when wind favored. Fear was part of the weapon. Enemy fleets learned to break formation at the sight of a fireship, to lift oars and turn, to disorder themselves in the very moment when order matters most. Technology and psychology braided. On land, the most frightening machine spoke a different language: gravity. A counterweight trebuchet is the plainest demonstration of potential energy you'll ever meet. One end of a long arm carries a sling and a stone. The other end carries a massive, hinged box of rocks, the counterweight that drops when a trigger pin is pulled. The geometry converts the slow fall of that weight into a high-speed arc at the sling tip. The release cord slips the noose from a horn at the precise angle set by the crew, and the stone becomes a meteor. If you've ever watched a child with a sling, you know the trick. The sling multiplies the arm's effective length, whipping the payload faster than the beam itself can move. Now scale that with timber and a falling ton. The counterweight is hinged so it can hang vertical as the arm rises, keeping the load path clean and the energy transfer efficient. The frame, a forest of struts and braces, absorbs the recoil with creaks and groans that tell an experienced chief exactly what to tighten before the next shot. Replace twisted rope torsion, the old catapult's power source which fatigues and drifts with gravity, and you replace moody caprice with repeatability. The earth does not forget how to pull. Accuracy is not magic, it's iteration. Crews mark release pegs in chalk, count their winching strokes, weigh shot stones, and walk their aim onto a target, across volleys left a meter low too. By the second afternoon, a good crew can put boulders into a small patch of wall until masonry opens like a book. When the English built Warwolf in 1304 to reduce Stirling Castle, it wasn't a stunt, it was state-of-the-art intimidation. The legend says the garrison offered to surrender at the sight of it. Edward I made them wait so he could use the machine. That's politics embedded in leverage. It's tempting to see only destruction, but the trebuchet is applied math under pressure. Pick your arm ratio. Longer sling side means higher release velocity. Shorter means a snappier cycle but less speed. Tune your counterweight mass. Too light, and stones dribble. Too heavy, and frames shatter. Shape your sling pouch so the stone departs clean, not tumbling at a bad angle. Cut your release pin with a bent tip so the sling slips at a predictable release angle. Then adjust the bend half a finger until range and arc match your siege plan. This is a parametric machine built by carpenters. And like the mill, the trebuchet is a platform. Swap stones for ceramic pots filled with quicklime or pitch. Now you throw blindness and fire. Throw dead animals in an early form of biological harassment. Throw messages over a wall or back to a besieging camp. Throw smaller stones in clusters like a shotgun blast to shred defenders on a parapet. The device doesn't care, it just turns height into speed. If the sea weapon depended on secrecy, the land weapon depended on spectacle. Building a great trebuchet is theatre, tall frames rising against a sky, ropes snaking across a field, teams on capstans singing to keep cadence, while the arm groans down against its will. Each crank stroke banks potential energy. The pause before the pin is pulled is liturgy. When the shot flies, the entire valley hears the report, a wooden thunderclap, then the delayed boom of impact. War is a story you tell your enemy about inevitable outcomes. The trebuchet writes that story in masonry dust. There's also an ethics of design lesson tucked into both weapons. They make the most of free forces. Fire wants to burn, gravity wants to fall. The engineering problem is one of containment and timing pump seals that don't leak under heat, frames that flex but don't rack, hooks that release when they should and never before. Notice what's absent: clockwork complexity, exotic alloy, machine precision. The tolerances are wood tolerances. The materials are local. The cleverness is in understanding what not to fight. If you look closely, the two systems rhyme. The Greek fire crew and the trebuchet crew both turn messy human effort into smooth, repeatable output. Pump teams keep a pressure wave steady because range depends on it. Winch teams keep cadence because missteps load frames unevenly and snap joints. Officers are not only commanders, they are conductors, keeping the orchestra in phase with the machine. Failure modes? Plenty. A gust can blow liquid fire back toward its makers if wind is misread. A failed leather seal can spit flame where flame should not be. Trebuchet frames split along a grain floor, pins gall and seize, slings tear, a bad stone bursts off the arm like shrapnel. That is why procedures matter. The Byzantines wrapped their weapon in protocols. Siege engineers wrapped theirs in checklists. Inspect slings, wipe pins, listen to frames, rotate crews, keep water and sand at hand for unwanted fires, keep wedges and spare timbers stacked near the footings. Medieval engineering is modern engineering with less metal and more memory. The legacy of these machines didn't end when cannons arrived. The trebuchet remained relevant wherever powder was scarce, and even today it lives on in physics classrooms and backyard fields because it is transparent. You can see the energy budget move. Greek fire's chemistry seeded centuries of interest in petroleum warfare and pressurized delivery. Its hydraulic insights migrate into firefighting pumps and fountains, into any application where a smooth stream matters more than raw volume. What these weapons say, loudly, is that ingenuity thrives under constraint. If you don't have niter, sulfur, and charcoal Standardized into corned powder, you teach stone to fall faster. If you don't have engines, you give air teeth and throw it on water. If timber is your primary structural material, you learn how it complains before it fails, and you teach your crews to listen. This is not romance. It is method. Choose the force the world will give you. Build a container that lets that force do clean work. Rehearse until the messy human part becomes as regular as physics. In the next chapter, the violence recedes and the geometry stays. We will step under vaults and between buttresses to watch stone carry itself like muscle, load lines flowing around glass instead of through it. The Trebuchet showed that gravity can destroy with precision. Gothic structure will show that gravity can be persuaded to hold light in the air. Same force, different promise. Walk into a Gothic cathedral and everything in your body recalibrates. The floor tilts subtly into height. Your neck is invited upward, and the air seems thinner because the stone has been coaxed to move where air wants to be. What looks like ornament is often structure. What looks like grace is often calculation. Gothic architecture is not a style slapped on top of masonry. It is an entire structural language, a way of composing stone to manage forces so intelligently that walls could become lace and light itself could be taught to behave. To understand the breakthrough, begin with a problem. Masonry loves compression and hates tension. A heavy roof will push outward on a semicircular Roman arch. That outward thrust wants to peel the wall apart. The Roman solution was brute mass thick walls, buttresses close to the line of the building, and pervasive solidity. That produces dark, earthbound interiors. Gothic builders wanted something else: vertical light, airy interiors, tall windows, and slender walls. They needed to turn outward thrust from enemy into obedient guest. The solution was a set of innovations: pointed arch, ribbed vault, flying buttress that together redirect forces instead of resisting them with bulk. First, the pointed arch. Unlike a semicircular arch whose thrust spreads widely, a pointed arch channels loads more downward than outward. That sounds like a minor tweak, but it changes the algebra of forces and frees walls from bearing so much lateral load. Pointed arches also provided a geometric advantage. They could span different widths with similar heights, allowing vaults to meet along complex plans without forcing awkward geometry into the roofline. Think of the pointed arch as a conversationalist with gravity, saying, "I will accept your burden, but I will hand it more politely toward the ground." Second, ribbed vaulting. Imagine the vault of a nave as a tent. Without ribs, the tent fabric would need to be heavy to hold shape. Ribs are the poles under the tent. A network of stone ribs create a skeleton. The skin between ribs, the webbing, can be much thinner. The ribs concentrate compressive forces into lines that can be carried down columns and piers directly to the foundation. This skeletal logic reduces weight and gives builders control. You can change the pattern of ribs to change how forces flow, much like a structural engineer draws load paths today. The ribs also create a predictable grid for masons to place panels and to coordinate teams. Where ribs meet, bosses, often carved, tie the system together. Those bosses are both decorative and, crucially, nodes of structural intersection. Third, the flying buttress, the element everyone pictures when they think Gothic. It is tempting to call a flying buttress a dramatic flourish, but that diminishes its function. A flying buttress is an external arch that catches the horizontal thrust from the vault and carries it away from the wall to a massive pier standing apart. The buttress bridges the outward force over an open space, often a clerestory window, so that the wall between buttresses can be a curtain of glass. The buttress itself is not merely a single arch, it is a composite system. The flyer, the arch, the pier, the heavy support, and the pierced openings that reduce weight and allow circulation while preserving load paths. This system has brutal elegance. By treating the thrust as a beam that can be carried externally, Gothic designers liberated the interior from the obligation to resist. The wall's job shrank: keep out weather and hang glass. The Buttresses' job expanded, act as a structural partner, tuned by mass, geometry, and placement. Where you place the buttress matters. Move it a few feet, and the load path changes shape. Wrong placement invites bending moments and cracking. Medieval masons understood this through apprenticeship and rule of thumb, not by finite element analysis. They tuned proportions, pier thickness, flyer curvature, pinnacle mass, until the system sang under wind and snow. Pinnacles deserve a paragraph, because they are a subtle trick, often read as decoration. A pinnacle is a weighted finial set, atop a buttress pier. Its mass pushes the pier down more firmly into its footing, reducing the chance that lateral thrust will tip the whole assembly outward. In other words, decoration that is also a counterweight ornament as structural insurance. The Gothic mind loved such dual use, beauty that earns its keep. Construction sequence matters as much as geometry. You cannot throw up a rose window in a half-built nave and expect the walls to behave. Cathedrals were built slowly, decade by decade, so that temporary scaffolding and wooden centering carried forces during construction. Labours were staged, foundations first, piers and inner arches next, then vault ribs, then webbing, then buttresses. When the work was executed correctly, seams and joints align, so loads are transmitted cleanly. When it was not, when ribs misalign or mortar fails, cracking can run like a fault line through stone. The masons monitored these lines with plumb bobs, simple templates, and their practiced eye. Geometry was tactile. You learned it through rope, compass, and muscle. Another marvel is the use of proportional systems ratios that tied the height of the clerestory to the width of the nave, the spacing of piers to the span of vaults, and the mass of piers to the expected thrust. Gothic design is not random ornateness, but a language of proportions that ensures that, as one element gets larger, its partners adjust accordingly. Look at Chartres. The choir rises in a stair of proportions that encoded structural rules and liturgical intentions alike. The cathedral is a machine designed for both theology and gravity. Material choice is part of the strategy. Builders selected stone for its compressive strength and weather resistance. Masonry units were cut to fit, often with massive accuracy, and assembled with lime mortar that allowed micro-movement but held in compression. Timber linings and temporary centering supported vaults until the ribs could knit the structure into a self-supporting shell. Metal was used sparingly. Cramps and dowels held stones that risked sliding, but iron was expensive and vulnerable to corrosion when exposed. Instead, the structural story is told mostly in geometry and stone, not in steel. Consider the rose window again as an instructive microcosm. A great rose is not merely a disc of colored glass, it is a load-bearing diagram. The tracery, the stone web, divides the circle into rings and spokes that channel compressive forces around the opening and into the surrounding wall. The tracery's geometry must align with the vaulting above and the buttresses beyond. Otherwise, the system becomes a concentrated weakness. Glass itself plays a role in the internal climate. It admits light and, by varying color, modulates illumination to favor certain liturgical loci. The window is thus a piece of material science, optics, and statics, all in one. What is remarkable is how medieval markets, ecclesiastical ambition, and guild practice combined to produce these innovations. Cathedrals were expensive civic projects, sustained by donations, indulgences, tolls, and the labor of guilds who saw their names and crafts immortalized in bosses and carvings. That economic fabric mattered. Guild rules, standardized training, shared techniques diffused across regions. Masons' marks, chisel signatures left on stones, allowed tracking of workmanship and payment. The cathedral is as much a social technology as it is structural. Gothic architecture also encodes humility. The system assumes cracking. It expects thermal movement, settlement, wind. That is why redundancy is baked in. Multiple ribs, paired buttresses, layered arches. Instead of pretending the building will never experience stress, The design makes paths for stress to move harmlessly. When a vault cracks, the crack is often arrested by intersecting ribs. When a wall settles, a nearby buttress can catch the misdirected load. This is engineering that plans for failure and turns it into recoverable damage. The legacy matters today. We call skyscrapers modern cathedrals, but the conversation with gravity is the same. Steel frames and glass facades are new materials. Their structural grammar, frame, column, moment connection, serves the same objective: carry loads where the material likes to carry them. Gothic builders reached that objective with different tools but similar reasoning. Align form with capacity, route loads efficiently, plan repairability, and acknowledge the environment. Walking out of a cathedral at dusk, you may find the light has changed and your body has relearned a posture of reverence. That posture is part aesthetics and part structural pedagogy. Buildings that teach people how to stand in them are doing social work. Gothic cathedrals taught a medieval population how to live under stone that reached for heaven and was pragmatic about the ground. The physics is precise, the theology is rhetorical. The combination is why, after centuries, these structures still instruct us on how to combine aspiration with discipline. In the chapters ahead, we will narrow the lens from whole buildings to the elements inside them: glass, color, and material science, and then swing towards smaller machines that ordered knowledge: clocks, astrolabes, and the mechanized analog mind. Keep this in mind. When you see airy walls and flying buttresses, what you are seeing first is a conversation with force, a polite, deliberate negotiation that lets light in by respecting stone. Stand beneath a great rose window, and your eyes do what the builders intended. They lose their appetite for edges and begin to read in radiance. The room stops being filled by walls and is, for a moment, filled by light given shape. That is the rose's first trick, turning illumination into architecture. Its second trick is quieter. The window is a load-bearing diagram, a structural device that persuades an enormous whole not to become a failure, but to become music. Begin with the problem. A wall carries compressive loads well because masonry likes compression. Cut a circular void 6, 8, 10 meters across, and you have interrupted the stress field. Where does the weight go now? An ordinary answer is, make the wall thicker. The Gothic answer is, draw the loads. Tracery stone ribs inside the circle acts like a wheel with spokes and rings. Each spoke siphons compressive force around the void into surrounding masonry. Each ring ties the spokes together, so forces distribute instead of concentrating. Where rings meet spokes, nodes form. Thicker stone, sometimes carved as bosses, that function like knuckles, preventing cracks from propagating. It is statics in filigree. This is why a rose is not merely decorative. The pattern is not freehand. It is parametric geometry done with rope, compass, and a mason's mental math. Starting from a center, the designer strikes circles, divides them into equal arcs, and inscribes polygons. Petals, lobes, cusps. These are not whimsy. They are solutions to where stone must be continuous and where it can be perforated without losing integrity. Change the number of divisions, and you change the path by which gravity gets home to the ground. Tracery itself evolved. Early plate tracery treated the wall like a stone plate perforated by holes. The openings are subordinate to the plate. Later, bar tracery treated tracery as a lattice of slender stone bars assembled to define voids. The bars read as structure, and glass area grows. That evolution isn't merely stylistic. It is a refinement of load paths. In bar tracery, each bar is a mini-beam in compression, and sometimes in bending, and its profile, often a complex molding, is as much about depth and stiffness as about shade and shadow. Now add wind. A large glazed disc is a sail. The rose must resist suction and pressure as gusts thrum the facade. Medieval builders answered with saddle bars, horizontal or radial iron bars that hold the glazing panels against the tracery, and ties that transfer wind loads back into stone. Lead cames, the H-shaped strips that grip glass pieces, are supple enough to accommodate movement, The system is a negotiation between rigid stone and forgiving metal. It survives because nothing is asked to do what it despises. Stone compresses, glass transmits light, lead flexes, iron braces. Glass is the window's soul, and medieval glass is not modern float. It is pot metal glass coloured in the melt, poured and blown into a cylinder, slit and flattened, or spun into a crown. It is streaky, with bubbles and striations that catch light like a frozen stream. Colour comes from metal oxides, cobalt for the legendary deep blue of Chartres, copper for greens, manganese for purple, iron for ambers and greens, gold and silver compounds for later silver stain that paints yellow into clear glass. Painters laid grisaille black-brown vitreous paint onto the glass to draw line and shadow, then fired the pieces so the paint fused. The result is not a picture placed on a window, it is a window that is the picture. A rose must do optics as well as statics. In morning light, the glass reads one way, in evening, another. Builders understood that different orientations demanded different tonalities. North roses lean into cooler palettes and iconography suited to contemplative gloom. South and west blaze at the hours when sun becomes a theological actor. The window is a clock of colour. Its program, apostles, elders, prophets, wheels of the cosmos, turns with the sun, teaching by slow saturation. Stained glass is not a medieval PowerPoint slide. It is a time-based medium. Look closely, and you see intelligence at the scale of millimeters. Thick glass reads darker because it absorbs more light. Thin, flashed layers can be abraded to create highlights. Pieces are cut so that lead lines stitch seams where the eye expects shadow around drapery folds, halos, architectural frames inside the image. The painter is also an engineer, placing joins so they reinforce the visual structure that the stone must carry physically. When the icon shows a wheel within a wheel, the tracery behind often echoes that wheel, symbol and stress rhyme. The installation sequence matters. You do not set glass into green mortar or wet stone. You wait until movement has slowed, then trace and fit each panel to its bay. Panels are built on tables to templates taken from the tracery itself, mason and glazier, in dialogue. Tolerances are real. Too tight and thermal expansion will crack glass. Too loose and wind will rattle it to death. Glaziers butter cames with putty to seal against water. They tie panels to saddle bars with soft wire so the assembly can flex without tearing. Maintenance is baked into the design. Leads will fatigue after centuries. Bars will corrode, pieces will bow. But each failure is local and repairable. Conservation today is its own chapter of craft. Iron bars swell as they rust and crush stone sockets. Restorers sleeve them or replace with stainless. Condensation breeds crusts on glass. Microventing and protective glazing can mitigate without suffocating the window. Bad 19th century restorations, overpainting, recutting get unwound piece by piece. The ethic mirrors the Gothic original. Intervene as lightly as possible, respect material, plan for future work. When Notre Dame burned, fire ate timber and lead. Heat crazed some panes. Yet the roses endured testimony to redundancy and to a system that allows damage without precipitating collapse. There is an acoustics subplot worth hearing. A rose, by admitting patterned light, also shapes sound indirectly. The vast voids of a cathedral swallow and scatter voices. The great stone web and its mullions diffract and reflect in small, complex ways. Medieval choirs learned to sing with the room, letting sustained tones bloom where reverberation favors them. Light and chant become a single instrument. The window participates without a single moving part. Economics threads through the glass. Sand, flux, wood ash, plant ash, fuel for the furnace, metal oxides, all had to be sourced, transported, traded. Glass houses burned through forests. Some shifted to brush and bracken. Guilds regulated recipes and guarded tricks. Donors paid for bays and requested saints in return. At the foot of a panel, You sometimes find a donor portrait, tiny figures kneeling, forever under a wash of colored light, their coins purchased. Technology here is paid for by piety and vanity in approximately equal measure. The rose also had a didactic job in illiterate societies. It is a diagram of the cosmos. The center often holds Christ or Mary. Rings radiate orders of angels, apostles, prophets. Outer bands carry earthly labors and zodiac signs. It teaches hierarchy without a word. But note the paradox. The most authoritarian content is delivered by the most democratizing medium, sunlight scattered across a crowd. Everyone stands in the same wash of color. Medieval theology and physics keep surprising company. What can a modern builder steal from this? First, the pairing of form and force. Do not cut a hole and then hope. Design the hole so that what remains is a structure, not an absence. Second, the acceptance of movement. Let stiff meet, flexible, with a mediator lead, in the medieval case, so that systems age by bending, not by breaking. Third, understand that experience is a function. The window is not an afterthought. It is the building's interface, controlling mood and attention as surely as a lighting designer's board. It is fashionable to compare the rose to a screen, and the metaphor works, with a twist. A screen emits, a rose filters. Emission flatters control, filtration flatters place. What you see in a rose depends on weather and hour variables outside your command. That surrender is not a weakness. It is a pedagogy, a reminder that good architecture collaborates with phenomena instead of counterfeiting them. In an age of total control, the rose argues for curated unpredictability. Stand again beneath the window. Notice how your eye rides the stone lines outward and then is caught by color and thrown back to the center. That motion is not accident. It is the builder's hand on your attention, guiding you between structure and story, weight and light, the seen and the felt. The rose succeeds because it fuses these domains into one intelligible object. It makes physics legible and belief visible. After 8 centuries, it still works because the laws it exploits have not changed. Gravity is patient, glass drinks light, and human beings remain susceptible to awe when a room convinces us that heaven has a geometry. Soon the scale will shrink from walls of color to mechanisms of time. We will leave the nave and sit with gears and brass, where falling weights become ticks, and the sky becomes a handheld map. The rose taught us how to draw light through stone. The clock and the astrolabe will teach us how to draw order through motion. When a weight falls in the dark, and a bell answers with a measured strike, something larger than sound happens. Time, once tied to sun, season, and appetite, acquires teeth. A mechanism has discretized a continuum. A smooth flow becomes a sequence of ticks. That is the signature of the medieval clock. Pair it with a brass disc that turns the sky into a handheld diagram to the astrolabe, and you have not just instruments, but a new habit of mind. Reality rendered calculable by gear and plate, by alignment and notch. The analog world is being made speakable in parts. The earliest mechanical clocks were born in monasteries, where prayer kept a strict schedule and cloud or winter made sundials useless. The problem is precise and stubborn. A falling weight wants to accelerate. A bell wants a steady cadence. Enter the escapement, a little genius of stop and go. The earliest common form, the verge and foliate, is a vertical staff, the verge, with pallets that catch the teeth of an escape wheel. Each tooth pushes a pallet, turning the verge. The opposite pallet then blocks the next tooth until the verge's oscillation returns it. Above, a foliot, a horizontal bar with adjustable sliding weights, governs the rate by inertia. Move the weights outward and the oscillation slows. Move them inward and it speeds. The escapement converts a weight's headlong fall into quanta of release. Tick, tock, an algorithm in iron. These first clocks were large iron frames in towers, their innards open to weather and pigeons. Accuracy, by modern standards, was poor, often off by minutes per day, but the existence of a consistent tick changed life. Bells regulated monastic hours, then market times, curfews, and civic routines. If watermills were the birth of automation, clocks were the birth of synchronization. A town now shared a rhythm. Merchants could schedule, courts could convene, labor could be counted. The clock pulled time off the celestial sphere and installed it in the square. Clocks also taught maintenance as a civic discipline. Iron rusts, teeth wear, ropes fray. The keeper of the clock listened for drift. A bell striking early, a tick that hesitates. He knew which pallet needed filing, which pivot wanted tallow, when frost thickened grease. This is not trivial sentiment. It is the embedding of feedback into daily life. A mechanism cannot be forgotten like a sundial. It must be tended, and that tending produces a class of people who think in tolerances. The philosophical shift is larger. The escapement didn't just regulate a wheel. It digitized time, converted a continuous variable into countable events. This prepared the ground, psychologically and practically, for later mathematics and finance that required granular units, interest rates, wages per hour, timed contracts, standard workdays. Even theology felt the nudge. Sermons about redeeming the hour, not merely the season. The clock did not create modernity, but it gave modernity a metronome. Move now from the tower to a table lit by a candle. A brass circle lies there, weighty and engraved. The astrolabe. It is, at heart, an analog computer for spherical problems. The back, the mater, or mother, holds interchangeable plates, tympans, engraved with coordinate grids for different latitudes, altitude circles, and azimuth lines, projected by stereographic projection. Over this sits the ret, a cutwork star map showing key stars as pointers, and the ecliptic as a ring broken into zodiacal signs. On the front swings a rule, on the back an alidade sight with pinnules for taking bearings. How does it work? Hold the instrument by its ring, sight a star along the alidade, read off its altitude above the horizon. Set the rete to rotate, so the star's pointer sits at that altitude over the correct azimuth on your plate. Now the whole sky is arranged. From this one act, time and position fall out like fruit. You can read local time at night, or measure daytime solar altitude, by aligning the sun's position on the ecliptic. You can estimate latitude by the height of Polaris in the north. You can find the rising time of a given star, the length of daylight for a date, even solve surveying tasks, and lay out Qibla, the direction of Mecca for prayer. Each solution is a mechanical inference: rotate, align, read. This is mathematics without algebraic notation, embodied instead in brass. Its elegance comes from the projection. Stereographic projection takes the spherical sky and maps it onto a plane, so that circles of altitude and azimuth become circles and arcs that can be cut and read. It preserves angles, which is exactly what you want for navigation and timekeeping. You don't need to know the theorem, you need to trust the tool. Yet using it teaches a kind of geometry you can feel. The instrument's career runs through the medieval Islamic world, where astronomers perfected designs, computed star tables, and wrote didactic treatises before it travelled into Latin Europe through translation and craft exchange. The astrolabe is thus also a story of knowledge circulation, how guilds and scholars harmonized across languages by means of metal and diagram. In that sense, it is a better model of progress than a line pointing upward. It is a tapestry of borrowings, each culture adding plates, scales, and uses. Accuracy, again, is relative. A skilled user can read to half a degree. A careful maker can engrave with even finer precision. Error sources, imperfect latitude plates, bent rules, parallax in sighting, temperature warp, are real, but the device is robust against them because its purpose is sufficiency, not perfection. Mariners later moved to the mariner's astrolabe, heavier, with fewer moving parts, designed to be read on a pitching deck, and then to quadrants, backstaffs, and sextants, as needs and accuracy demands grew. But the logic holds. reduce a complex celestial relationship to a small number of mechanical motions. That is computing. Put clock and astrolabe side by side, and you get a duet in representation. The clock turns gravity into uniform intervals. The astrolabe turns the sky into uniform relationships. One is a regulator, the other an interpreter. Both offer interfaces with reality that non-specialists can learn. Ring the bell on the hour, not after eyeballing the sun. Read the rete instead of running spherical trigonometry in your skull. This is democratization by device. They also seed an ethic of standardization. Hours become countable units across town. Latitudes become shared numbers across charts. With standard units come contracts, schedules, appointment books, tides tables, and ephemerides. The social math thickens. A market opens at the third bell. A ship departs when the sun is 3 degrees high. The gradual migration from embodied, local cues to portable, abstract cues doesn't erase the local, it coordinates it. That is a quiet revolution. There is beauty in their failure modes. A clock runs fast in winter because grease thickens. You learn about materials. An astrolabe lies to you near the horizon because refraction lifts celestial bodies. You learn about air. These devices do not hide their assumptions. They let you feel them. In an age that treats black boxes as magic, the medieval instrument is pedagogical, transparent enough to criticize and to repair. The lineage forward is obvious but worth tracing. The escapement's logic sample, hold, release, reappears in sampling theory, in flip-flops and digital clocks. The idea that a steady oscillator plus a divider yields stable time becomes quartz and atomic timekeeping. The Astrolabes logic project, a line, read becomes slide rules, nomograms, circular calculators, aviation E, 6Bs, even UX patterns, set 2 controls, read a third value. When you scroll a star map app at night, you are turning a digital rete over virtual timpans. The ghost of brass is in your hand. Were these medieval devices primitive? Only if we mean Primer's first textbooks in the mechanization of thought. They taught societies to trust procedures, to encode experience in mechanisms, to accept that good enough, repeatably, is a kind of power greater than brilliant once. They also taught that care is the cost of intelligence embodied in matter. You wind a clock because forgetting is time's natural state. You clean an astrolabe because the sky deserves a clean mirror. Maintenance, once again, is part of the algorithm. Step back, and the pattern we've been tracing all along comes into focus. The mill, the trebuchet, the buttress, the rose, the clock, the astrolabe, each takes a continuous world and builds handles for it. Water becomes torque, gravity becomes velocity, thrust becomes arch, light becomes icon, duration becomes ticks, the sky becomes a dial. None of this required electricity. All of it required abstraction disciplined by craft. In the final chapter, the lens widens. We'll gather these threads: durability, adaptability, repair, fit, and ask what we have forgotten about progress. The past does not demand that we return to weights and candles. It asks a sharper question. Can we build as if time, place, and users matter as much as speed? The answer will not be found in nostalgia. It will be found in pacts we write with materials and with each other, the kind Romans and millwrights and glaziers once honored as a matter of course. We tell ourselves that progress is a straight road, always forward, always upward, paved with better materials and brighter screens, but stand long enough in the ruins of anything we once called new, and another pattern appears: asphalt cracks, plastics yellow, screens go dark when their makers stop releasing updates. Meanwhile, Roman piers still face the sea, Gothic arches still hold their breath in mid-air, medieval clocks still mark hours to no audience at all. This is not a paradox. It is evidence that progress is not momentum, it is memory, and memory is exactly what we keep throwing away in the name of efficiency. The civilizations we've walked through in this story built slowly because they had no choice. Every material they used demanded patience. Lime took months to slake, Timber took seasons to dry, stone took generations to set. But the constraint was the gift. To build under those conditions forced a kind of intimacy with time itself. A mason couldn't afford illusions about permanence, so he built for repair. A millwright knew every gear would rot someday, so he made sure every pin could be replaced by hand. A glazier accepted that sunlight would fade pigment, so he designed windows that could be disassembled and reborn. The pre-modern world did not dream of immortality. It practiced endurance. Modernity, for all its brilliance, traded that endurance for velocity. We learned to mass-produce miracles, and in doing so, we unlearned the logic that once bound making to meaning. Planned obsolescence became not just a business model, but an ontology, a worldview where even people are consumable after a few cycles of usefulness. The same logic that tells us to upgrade our phones every 2 years also governs how we build cities, how we treat soil, how we design software, how we measure success. We praise innovation while quietly depending on fragility. It is a strange progress that leaves us surrounded by things newer than ever yet older in spirit, decaying faster, lasting less. The blueprint we lost is not a recipe, it is a philosophy. The ancients and medievals did not worship technology, they participated in it. They built as if the world were alive and would one day speak back. Roman concrete healed itself, not because they stumbled into chemistry, but because they mixed materials that wanted to live together. Lime that wanted water, ash that wanted crystal, geometry that wanted rest. The Gothic cathedral stood because its builders accepted gravity as a partner, not an enemy. Even the Trebuchet, born for war, functioned through cooperation with gravity, not defiance of it. Their machines mirrored natural systems, slow, resilient, cyclical. Ours mostly imitate our appetites, fast, restless, terminal. We often talk about sustainability as if it were a new moral invention, but in truth, it is an old instinct modernized beyond recognition. To a medieval farmer, sustainability meant survival. To a Roman engineer, it meant minimizing risk over centuries of wear. They did not have climate models. They had weather. They knew wind could change, rivers could flood, timber could split. So they designed for imperfection. Today, with satellites and simulations, we design for precision instead. We aim to erase uncertainty through control, forgetting that control itself is fragile. A power grid fails faster than a water wheel. A cloud server dies quicker than a parchment. Progress has taught us to measure everything but patience. If there is a thread running through all these forgotten technologies, it is the willingness to think long. Roman harbors, Gothic vaults, Islamic astrolabes all required a faith that the future would still care. It was a form of collective optimism written in stone and brass. We build differently because we expect abandonment. We assume our successors will want to tear down what we raise, so we make sure it can be done easily. That assumption becomes self-fulfilling. Nothing lasts because nothing is meant to. We treat durability as a vice, nostalgia as weakness, and craftsmanship as inefficiency. Yet when disaster comes, earthquake, flood, fire, we suddenly crave what we once dismissed. Systems that fail gracefully, buildings that breathe instead of break, materials that forgive us for being human. The medieval craftsman would not have recognized our concept of innovation. To him, improvement meant refining what had already proven trustworthy, not discarding it. Each generation was an editor, not an inventor. That slowness gave stability to knowledge. The apprentice who carved his first arch in the 12th century could still recognize the same curve in the 15th. Today, we reinvent everything from scratch because we have forgotten how to maintain continuity. We call it creativity, but much of it is amnesia. We have mistaken novelty for progress and disposability for evolution. The true cost of that forgetfulness isn't just environmental or aesthetic, it is spiritual. A civilization that builds disposable things eventually treats its own wisdom as disposable too. When our ancestors looked at their work, they saw collaboration between body and matter, stone teaching hand, hand teaching stone. That dialogue produced humility. You couldn't bully granite, you had to negotiate with it. In that negotiation, they found meaning. We, on the other hand, build from a distance, robots pouring, algorithms optimizing, humans supervising screens. Efficiency rises, intimacy dies, and with it goes reverence for the real. So, what would it mean to recover the forgotten blueprint, not as romance, but as practice? It would mean designing for repair, not just performance. It would mean accepting that beauty is not decoration but evidence of care. It would mean planning for time as a collaborator, not an adversary. A product that ages well is an ally in patience. A building that can be maintained with simple tools is an act of democracy. True progress would measure success not by how quickly we can replace something, but by how gracefully it can endure and adapt. To build that way, again, doesn't require rejecting technology. It requires reteaching it what to value. Modern materials are not the enemy. Concrete can heal again. Algorithms can preserve. Machines can serve longevity instead of turnover. But they will only do so when we, their makers, rediscover a sense of obligation to the future. The ancients didn't need sustainability manifestos because their daily survival was manifesto enough. We, cushioned by abundance, need stories to remind us why stewardship matters. That is what history is for, not nostalgia, but calibration. If there's a single moral to draw from Roman piers and Gothic arches, from windmills and waterwheels, from astrolabes and clocks, it's that intelligence in matter always mirrors intelligence in ethics. A structure that holds itself together under stress is a metaphor for a culture that can do the same. When we design without moral imagination, we build without structural imagination. When we treat time as an enemy, our buildings betray us in kind. The blueprint we lost is therefore not a diagram of walls and arches. It is a worldview in which every act of construction was also a prayer that life could continue. And so we arrive where we began, at the edge of our own arrogance, surrounded by machines that rust faster than memory. Progress is real, but it is not innocent. It has given us power without purpose, acceleration without arrival. The past is not asking us to go backward. It is reminding us that direction matters less than intention. A civilization is not measured by how high it can build, but by how well it can listen to stone, to wind, to the hum of its own machines. If we listen carefully, we might hear that faint, ancient rhythm still echoing beneath our cities, the sound of a mill turning by water, of a bell ticking off a steady hour, of a craftsman's mallet striking stone. They are not relics, they are instructions. Build for those who will never meet you. Make time your collaborator, not your casualty. Because one day, long after the servers crash and the lights dim, the only proof that we were truly advanced may be how much of our work still stands quiet, patient, and alive with the wisdom we once remembered how to build into it. You've just walked through another forgotten corner of the past, not the world of kings or saints, but the quieter country where most of humanity has always lived. The small rooms, the muddy fields, the faith that bends but doesn't break. These are the places where history truly breathes. Here at Poor Historian, we don't chase the noise of glory. We listen for the whispers, the sound of a wooden spoon scraping the last meal from a pot. The hush before a bell tolls the breath of someone still alive after everyone richer has gone. The poor never wrote their stories, so we try to lend them a voice slow and steady, the way truth prefers to travel. If you've stayed this long, perhaps something in those voices found you. Maybe you recognized a little of yourself in their endurance, the quiet act of getting up again, of doing the work that no one will ever sing about. That's what this channel exists for, to remind us that survival is not small, that dignity can live in the dirt, and that memory is the gentlest kind of rebellion. Take a moment before you go. Let the sound of their world fade but not vanish. Picture the candlelight softening the corners of a cottage, or the hush that follows when the last tool is put away. Those lives are long gone, but their echoes are patient. They wait for anyone willing to listen without hurry. If you want to keep walking these narrow paths of the past, the ones that smell of smoke, sweat, and stories, you can help them stay lit. Subscribe to Poor Historian and let history find you when the world gets too loud. Leave a comment if a scene or a sentence stayed with you. That's how we keep these voices alive. And if this journey brought you a little calm, a little wonder, or just a better kind of silence, share it. Someone else might need that stillness too. There are more lives waiting here. Peasants, healers, builders, soldiers, mothers, ordinary souls who made the Middle Ages anything but dull. Their stories don't demand attention, they earn it. Each one is another piece of the great mosaic of how we got here, not through brilliance or conquest, but through persistence. So as you close your eyes or drift into sleep, remember this history isn't only what was written, it's what was endured. And somewhere, in the dust between centuries, the poor are still telling their stories, softly, stubbornly, gratefully, to anyone willing to listen. Thanks for listening, for remembering, and for keeping company with the forgotten. We'll meet again in the next quiet story.